We have been discussing the Stern-Gerlach experiment in the previous classes, and in the last class we looked at the sequential Stern-Gerlach experiment. In the sequential Stern-Gerlach experiment, we saw that there are some things going on which cannot be really understood based on a classical logic. Our aim was to develop a mathematical framework, mathematical description for this kind of behavior, and to this end it will be helpful to look at an analogy, a classical analogy. It is the analogy with polarization of light. So in the sequential Stern-Gerlach experiment, it was seen that an electron cannot have a definite Sz and a definite Sx simultaneously. This was one of our conclusions because you could send one atom at a time, one silver atom at a time. And if you look at an atom with a definite value for Sz, okay, with a definite value of Sz, okay, call it Sz plus or plus h cross by 2. If Sz is equal to, this corresponds to, as we said, Sz is equal to plus h cross divided by 2. Okay. Now, if you try to measure the Sx value for this, all right, the x component of spin for a beam characterized by Sz is equal to plus h cross divided by 2, we would see that it is either Sx plus or Sx minus. We don't know which. Okay, it's with equal probability it could either be Sx plus, which means h cross divided by 2 along the x direction, or minus h cross divided by 2 along the x direction. Right? This is what we mean by an uncertainty. Okay? So if the Sz component is completely defined, then this becomes completely uncertain. All right. In the same way, if a beam is characterized by an Sx plus beam, right? In the same way, if the beam is characterized by an Sx value, right, which means that, let's say for example, that Sx is equal to plus h cross divided by 2, and now if you try to look at the Sz value, you see that it's completely uncertain. It could be either plus h cross divided by 2 or minus h cross divided by 2 in the z direction. All right, so you see that there's some sort of incompatibility between these two. Now, we also said that we made a statement that the selection of the Sx plus beam by the second apparatus, all right, so the second apparatus has actually selected an Sx plus beam. The selection of the Sx plus beam by the second apparatus, we called it as Sgx hat, it completely destroys any previous information about Sz. All right. So if you look here, previously we had the information that this beam is characterized by Sz plus. Okay. Now once we pass it into an Sgx hat apparatus, this information is lost, and now it could either be Sz plus or Sz minus. Okay, so this information is lost. Now, if you are not passing it to an Sgx hat apparatus, instead if you are passing it to an Sgz hat apparatus, you will get only one beam out of this, only the Sz plus beam. That information stays there. But once you pass it to an Sgx hat apparatus, this information is lost. All right, and then it could either be Sz plus or Sz minus. Okay, now a similar kind of thing is happening in the case of polarization. Okay, let's look at that. So because this situation looks so different, some analogy with a familiar classical situation may be helpful here. The polarization of light waves provides an analogy to this. This analogy will help us develop a mathematical framework for formulating the postulates of quantum mechanics. So basically, our aim here is to look at mathematical objects, all right? Look at mathematical objects that can describe such behavior as we see in the Stern-Gerlach experiments. Okay, such behavior as we saw in the SG experiments. This is our aim, right? We need to look for mathematical objects which can describe the kinds of things that are going on in the quantum mechanical world. So now we go to a classical case of a monochromatic light wave. Okay, so in classical field theory or electromagnetism, we consider light as a wave. All right. So you consider a monochromatic light wave propagating in the z direction. So you have got a light wave propagating in the z direction. This is purely classical picture. You are not talking about photons or anything. It's just an electromagnetic wave. Now a linearly polarized or plane polarized. So you might have studied already about polarization, etc. If not, it's fine. Okay, a linearly polarized or plane polarized light. Okay, what do we mean by polarized light? A linearly polarized light with a polarization vector in the x direction. Okay, which we call for short an x polarized light, has a space-time dependent electric field oscillating in the x direction. So this is what we call as an x polarized light. X polarized light. Okay, so from this argument you see that it's propagating in the z direction. The propagation is in the z direction, propagates along the z direction, whereas the electric field is along the x direction. All right, or the what is a space and time dependent electric field is actually oscillating in the x direction. All right, it's oscillating in the x direction. So if the oscillations are purely in the x direction, we say that it is an x polarized light. In the same way, if the oscillations of the electric field, we know that light is an oscillation of electromagnetic field, and we are looking only at the electric field here. Now if the oscillation of the electric field is along the y direction, we say that it's a y polarized light. We call it a y polarized light. So the direction of polarization, all right, the polarization is given by this unit vector here, whether it's in the x direction or in the y direction. All right. Now, how do we obtain such polarized light beams? It can be obtained by letting an unpolarized light. So light need not always be polarized. It could have what they say oscillations in all sorts of directions, but you can filter out the necessary polarization by letting the light go through a polaroid filter. Okay, so we can use polaroids to filter out certain components of oscillation. Okay. Now, a filter that selects only beams polarized in the x direction will call an X filter. Right? So, when light passes through an X filter, the output will be only those beams which are polarized in the x direction, exclusively in the x direction. Okay. So, when we let a light beam go through an X filter and subsequently let it impinge on a Y filter, no light beam comes out. Right? This is understandable because x and y directions are mutually orthogonal. Right? So, if you initially choose a light beam which is polarized in this direction, all right, this means that the polarization has no components at all in the orthogonal direction. All right, there are no components in the orthogonal direction. Okay, so you can see that here. Initially, you have got an unpolarized light. Okay, now out of the X filter comes an X polarized light. Right, comes an X polarized light beam. Okay. Now, if you pass this X polarized light beam into a Y filter, nothing comes out here. It blocks everything, all right, because the Y direction is orthogonal to the X direction. Now, you can denote it like this. These lines can be used to denote an X filter, right? So, the light, the filter, this particular filter will let through polarizations in this particular direction. Now, if the Y direction, the orthogonal direction can be denoted by lines which are perpendicular to this. Right? So we can say that by rotating the X filter by 90 degree, you can get a Y filter, etc. Okay. All right. So initially we choose this direction from the X filter. All right. Now since this direction is completely orthogonal, completely perpendicular to this direction, this polarized light passing through the second filter gives out nothing. There is no light. Okay. All right. Now the situation becomes interesting if we insert between the X filter and Y filter another polaroid. Right? So what we do here is that in this case, between this X filter and Y filter, you you insert another polaroid, another filter. You insert another filter in between. Okay. Now this filter will call an X prime filter. And what does an X prime filter do? An X prime filter chooses polarization in the x prime direction, right? And x prime filter chooses polarization in the x prime direction only. Okay. In this case, the second polaroid that we have, the third polaroid, all right, the polaroid that we have inserted in between is such that it makes an angle of 45 degree with the x direction, right? So if you have got this x direction and y direction, okay, that the x prime direction is this. This is 45 degree. All right, this would be the x prime direction. So what would this x prime filter do? It will let in only polarizations in this direction. Okay. Now, once we do this, all right, once we do this, what happens is that the light goes to an X filter. Okay, and you have only an X polarized light here. All right. So now instead of going directly to the Y filter, you pass it to an X prime filter. Right, and you will get an X prime polarized light beam out of it. Okay, so this X filter and the X and X prime directions are at 45 degrees of each other, which means that X has a component along the X prime direction. Right? X has some component along the X prime direction. They are not orthogonal. So certainly this will let in some light beam. Some light beam will come out here, and its polarization will be in the X prime direction. Right? Now, since the X prime direction also has a component along the Y direction. Right? So if you look at these are just vectors, right? These are just vectors. You've got X, Y, X prime. You see that the X prime direction has component with X direction as well as Y direction. Right? So for this reason, the Y filter also will give off some light. The Y filter will also give off some light. Okay. So without this X prime filter in between, there's no light coming out of the Y filter. But if you install an X prime filter in between, all right, the Y filter will give off some light beam. All right. So this time there's a light beam coming out of the Y filter, in spite of the fact that right after the beam went through the X filter, it did not have any polarization component in the Y direction. All right. So here there's no Y direction, no polarization component in the Y direction, no Y component. Here there's no Y component. But after passing through the X prime filter, it has picked up a Y component. It has picked up a Y component. So it's like saying, as in the previous case, in the Stern-Gerlach case, we said that the information that there's no Y component here is lost, it's destroyed once it passes through the X prime filter. All right, so the information available here is what? It is X polarized and there's no Y component. But once it passes through the X prime filter, the information that there's no Y component is lost. This information is destroyed and the Y filter picks up a Y component. Okay. All right. So once the X prime filter intervenes and selects the X prime polarized beam, it is immaterial whether the beam was previously X polarized. Right? It doesn't matter. The previous polarization doesn't matter. That information is destroyed. Okay. The selection of the X prime polarized beam by the second polaroid destroys any previous information on light polarization. Right? The information that is available, the information right here, okay, the information at this point is lost when it passes through the second polaroid. Now notice that this situation is quite analogous to the situation that we encountered earlier with the Stern-Gerlach arrangement. All right? In the Stern-Gerlach experiment, we used exactly the same kind of words. We said that some information is destroyed once it passes through a second Stern-Gerlach arrangement, etc. The same kind of thing is happening here. Right? So for this reason, maybe we can make a correspondence. It seems that the SZ atoms behaves like X polarized light in some manner, right? At least the words that we have used to describe these two situations, we can say that the SZ plus atoms are like X polarized light, the SZ minus atoms are like Y polarized light, okay, and the SX plus minus atoms are analogous to the X prime Y prime polarized light. Okay, so when I say analogous, it seems that the kind of mathematics that we use to describe this polarization, okay, the same kind of mathematics might be useful when we describe spins. Now let me make this analogy clear. Okay, let's look at the Stern-Gerlach, the sequential Stern-Gerlach arrangement first. So in the sequential Stern-Gerlach arrangement, we had a beam of atoms, a beam of silver atoms coming in, and then first we subject it to an SG Z hat apparatus, and we know that there are two components, an SZ plus component and an SZ minus component. Right? Now what I do is that I block this SZ minus component. Okay. Now this whole arrangement, if you look at it, it takes in what's the input? It takes in atoms Okay, we don't know what, all sorts of atoms, silver atoms, and then gives out only those atoms with Sz plus, which are characterized by Sz plus. Okay, so this I can call an Sz plus filter. Okay, why? Because it gives out only Sz plus, only those atoms which are characterized by Sz plus or plus H cross by 2 in the Z direction. Okay, so this is an Sz plus filter. Now what do I do with the output of the Sz plus filter? I put it into an SGX hat apparatus, and we know that there are two beams coming out. One is the SX plus beam and the other one is the SX minus beam. Again, I block this SX minus beam. This SX minus beam is again blocked. What do we have out here? Only the SX plus beam, right? Only the SX plus beam, only those atoms characterized by SX plus, right? So this arrangement altogether I can call an SX plus filter. Right. Now I can again analyze this beam using a Stern-Gerlach apparatus, SGZ apparatus, and we'll see that it has both components, SGZ plus, sorry, I think we denoted it as SZ plus and SZ minus. All right. So this SX plus beam has both SZ plus and SZ minus. All right. This can be understood by analyzing it using a Stern-Gerlach apparatus. All right. SGZ hat apparatus. So here it is only Sz plus, but after passing through the Sx plus filter, it has picked up an Sz minus component also. All right. Now, what did we do with the case of polarizations? We had an unpolarized light, Okay, unpolarized light. Okay. Now this goes into an X filter. We said goes into an X filter. What comes out is an X hat polarized light. Okay. Now this X hat polarized light is then fed into an X prime filter. All right. And what we get out of this is a light beam that is polarized in the X prime direction. Okay. Now, if we further analyze this in the sense that if we pass it through an X filter, we'll get an output. If we pass it through an Y filter, also we'll get an output. So this means that this X prime here, it has two components. It has an X component and a Y component. Even though here there's no Y component, after passing through the X prime filter, it has picked up a Y component. Okay, so this is the similarity here. So we see that the same kind of mathematics, okay, at least similar kind of mathematics, might be responsible in this case also. We already know the case of the mathematics that is responsible for this behavior. In the case of polarization of light, it's just classical field theory. It's electromagnetism. The mathematics of this we know, all right. So we are suspecting that there should be some similarity between the mathematics of these two arrangements, all right. Whether we are dealing with polarization or you are dealing with atoms, there seems to be some sort of similarity in the underlying mathematics, all right. So that's why we make the following identification or the analogy. We say that Sz plus is analogous to X here, right? So the Sz plus here is Z plus here is Z plus atoms. Let's say that Z plus atoms. We can say that they are analogous to the X prime, X hat polarization or X polarization. All right. And here we see that similarly the X prime, sorry, here we have got Sx plus atoms. These are analogous to the X prime polarization. All right. Now we could do exactly the same thing by blocking the Sz plus beam and then letting out the Sz minus beam. In that case, this would become an Sz minus filter. This could be taken as an Sx minus filter. And again, in the end, we'll get both Sz plus and Sz minus. All right. So here we have got Sz plus, here we have got X, here we have got Sz minus, here we have got Y. All right. So we can make further correspondence. So the other case is exactly the same. Okay, so we can say that Sz minus atoms I think I should write it somewhere here. Z minus atoms can be made analogous to Y polarization. Okay, a light beam with Y polarization, and Sx minus can be made analogous to Y prime polarization. Right? So the same kind of mathematics will then work out. That's what we have said here. Sz plus minus atoms are analogous to XY polarized light. Okay, and Sx plus minus atoms are analogous to X prime and Y prime polarized light.